Hi, this is kind of the introduction to parametric functions. And so I guess the first thing we want to do is what do we mean by parametric? And so when you think parametric, most of the time you're going to think time. Maybe you're going to think about theta eventually if you think about letting the angle vary. But really what this does is that we're going to look at the parameter. And in this case, it's going to be time. And instead of looking at y as the function of x, we're going to look at x and y both as individually functions of time. Y is a function of time and x is a function of time. And so when we start thinking about parametric functions, we're really talking about motion. In this case, we're talking about two-dimensional motion. We could do 3D, we could do x, y, and z, but the four examples that I kind of selected here are just two-dimensional examples. And the beauty of parametric equations is that we can describe so many things. We can describe starting position, we can describe horizontal position, vertical position. We can take derivatives and find horizontal and vertical velocities. We can take additional derivatives and find horizontal and vertical accelerations. We can find speed. We can find distance traveled. Again, when you think about an old function, y is a function of x. It was just kind of a graph, but it had no motion associated with it. There was no start. There was no speed. There was no distance traveled. It was just kind of a circle or a parabola, and it didn't really have any direction. This is all about modeling things, and typically what we're talking about here is motion. Okay, so let's kind of go through these examples, and we can just briefly start talking about what we all can look at in terms of analyzing it now that we understand calculus. So the parametric functions are x of t is 8t, and then y of t is 64 minus 16t squared. So this is an equation that's describing its horizontal position, and this is an equation that's describing its vertical position. You can look at those graphs if you want to, but let's just look at the equations first. So what are we doing horizontally? We're moving 8t. Well, what if I took a derivative and I looked at dx dt? Well, the derivative of 8t is just 8. I looked at dy dt, that would just be negative 32t. And in a physics classroom, what is dx dt? Dx dt is the rate at which we change our horizontal position. Well, in physics, we would just call that vx. It's just the horizontal velocity component. Dy dt, well, in physics, we would just call that vy. It's just the vertical velocity. It's the rate at which we're changing our vertical position with respect to time. It's just a derivative. And again, in a calculus classroom, they might use dx dt. In physics, they would just call it v subscript x, because that's all it is. I could take another derivative. We would call that, in calculus, we'd probably call x double prime, and that'd be 0, right? The derivative of 8 is 0. And then we get y double prime, and we would get negative 32. In physics, we just call this acceleration. This is the acceleration horizontally, and this is the acceleration vertically. And if you look at the motion here, x is some linear function with respect to time, and so it's got a constant velocity, right? Constant slope here. And it's got no acceleration because dx dt is some constant. So it's moving constantly 8 meters to the right every second, and it's not changing that, so it's got a horizontal acceleration of 0. Well, vertically, it's a quadratic. So then the vertical velocity, right, dy dt is some linear function, so it's changing with respect to time, and it does have an acceleration. It's got a negative 32 acceleration, so that might be in feet per second squared or meters per second squared. We won't really worry about the units here, but looking at this motion, I've already told you now, horizontal and vertical position as a function of time, meaning I can tell you where this thing is at any moment in time. I can tell you how fast it's moving to the right and or left. In this case, it's always just moving to the right. How fast it's moving vertically at any moment. And then I can tell you the acceleration in both components, in both the horizontal and the vertical. Right? We could look at graphs if we wanted to kind of look at this. If you looked at x of t, as a function of time, 8t, graphing x versus t, is just some line. And so look, it's got a slope of 8 and no changing of the slope. Right? It kind of confirms what we're doing here. If you look at y as a function of time, again, not y as a function of x, y as a function of time, this would just, well, if we just look at t greater than 0, lots of times we would set a domain restriction there. It would look something like this. Right? It's going to go down that way. Again, this is where we would start. We'd start up here at 64 because when I plug in t equals 0, I get 64. We start at an x value of 0 and we would grow. And really, what's happening here? Well, this was turned out, if you really analyze both of these motion at the same time, this is going to describe a situation in which you started at 64, height, and you're thrown out horizontally, and then gravity takes over, and you do something like this. This is the actual graph of the motion. Like, this is literally the path. But this tells us nothing. It doesn't tell us where we started. It just tells us horizontal position relative to a vertical position. This tells us everything we want to know in terms of a function of time, and that's what a parametric equation does. It uses the parameter t and then allows us to write separate functions that are both dependent on t. Okay, let's move over to this one. This one might actually be a little bit easier. Let's take derivatives here and investigate what's going on. So we get dx dt, well, that's just 6, and then dy dt is just 8. And so we look at it, x starts at 5, and it goes 6t, meaning the rate of change is 6. So that's what dx dt is, right? That's horizontal velocity. So it's moving to the right at 6, and it's moving up at 8. And actually, those things are constants, and so neither one of this motion has acceleration in either direction, right? So it's got this constant speed, and we could even find this speed. The speed, well, what is speed? We'll get into more in depth later, but speed will end up being the square root of dx dt squared plus dy dt squared. And that looks complicated. It's like, oh, is that some new formula I need to memorize? And I would say, of course not. Speed is the magnitude of the vector. Right, now, vectors. We are going 8 meters per second to the right. 6 meters per second to the right. And we're going 8 meters per second up. The speed is the magnitude of that triangle. If you're going 6 that way and 8 that way, aren't you really going the dotted line? And it does even have some angle associated with it. And we can use the Pythagorean theorem. And all this is saying is to find your speed is to take the square root of 6 squared plus 8 squared, which we know is then 10, right? Because it's a 3, 4, 5, that's 6, 8, 10, so 10. So our speed would be 10 meters per second, or feet per second, or whatever the unit would be. And then the angle, well, if we look at it, tangent of theta does equal 8 over 6, and then we could do inverse tangent of 8/6, okay, to actually find the angle. So we can do all sorts of another analysis based on this. And again, this is motion that we're moving this way. And if we wanted to look at a graph of it, well, we could. We could look at y versus x. And again, we could think about, well, where does it start? Well, when t equals to 0, where is it located? Well, it's 5 over and then 1 up. So it's like this. And then what do? Well, every second we move 6 meters to the right and 8 meters up. Well, actually the slope. The slope here, m, which is the same thing as dy dx, because we know that, is really just the ratio of dy dt over dx dt. And we'll do this more when we get to the calculus feature, but I figured we should introduce it now. The slope on this graph is how we're changing. And again, the slope here is this ratio. And that ratio would end up being 4/3, and so the slope here would be a little bit bigger than 1, and we would do something like that. If you wanted to figure out where you were at 1 second, well, you're at 11 and 9. Where you're at 2 seconds, that's just plugging in 2 here, and you're going to get, what, 17 and 17. You're just going to keep increasing, and you're going every 4 you go over this way, or excuse me, 3 you go over this way, you go 4 up, because that's the ratio of those two speeds, horizontal speed and vertical speed, or really their velocities, because they are vectors, horizontal velocity and vertical velocity. And then we just keep moving along. But again, this information is way better than the actual curve if you found y equals to x. Okay, let's come down here. So look what's happening here. Oh, that's probably a little sloppy. That's y of t. Okay, so horizontally, we're bouncing back and forth. What does that look like? Well, what if I drew x as a function of time and I do some cosine curve? I'm going to do that. So my horizontal position, I'm a cosine curve. I'm to the right, I'm at 0, I'm to the left, I'm at 0, I'm to the right. So I'm really bouncing back and forth horizontally. And then y, I'm just increasing, because the graph of y of t is pretty easy. I'm just going up with a slope of 5. So think about putting those together on yx curve, make that a little higher, y versus x, when t equals to 0, I'm at an x value of 3 and a y value of 0. So y value of 0, x value of 3, that's here. And then what happens? Well, y, I'm going to go up. Because remember, what is dy dt? Well, dy dt is just the derivative here. That's just 5, right? Hopefully you already have decided that the slope here is 5. And again, this is vertical slope because I'm taking the derivative of the vertical velocity, or the vertical position equation. Dy dt is 5, so I'm going to move up at 5. And it's going to be constant, so I'm not going to accelerate. And then this is going to make me bounce back and forth. So I'm going to weave through this thing like so, and I just keep oscillating back and forth as I go through time. And again, if I want to know horizontal velocity, I could take this derivative, well, the derivative here, dx dt is going to be a negative 3 sine t. Check that out. What happens to my velocity? Well, at the beginning, my velocity is negative. What happens? I'm moving left. See how I'm moving left? And then I'm moving more left, and then I move to the right. And then I move back left, and again, that's what this trig function will do. This trig function is going to go back and forth between a positive and a negative value because it's a periodic function. Well, it has to be. If your position oscillates back and forth and back and forth and back and forth, well, then you have to be moving left and moving right and moving left, which means your velocity function. In this case, it's just the horizontal that's going back and forth. We're always going up vertically, which is what this is saying. dy dt is equal to 5. And again, let's look at another one. Okay. So x of t is this, and y of t is 2 to the t. Let's take derivatives here. Let's look at dx dt. That's 2t. And let's look at this derivative, dy dt. And the derivative of 2 to the t is 2 to the t natural log of 2. Okay, so vertically what we're doing is we're going zooming away with some exponential growth vertically. And horizontally, well, what are we doing here? Well, it actually looks like at the beginning we have some positive value, and then our velocity, well, if we only look at positive time, we're always just moving up. We can look at x double prime, which was 2. We could take another derivative here and look at y double prime. And that would just be another factor of that. It's kind of silly to end up 2t times the natural log of 2 times another factor of the natural log of 2. And again, what are these? That's horizontal velocity, horizontal acceleration, vertical velocity, and vertical acceleration. And again, we'll talk more in depth on things like distance traveled, like if I want to find this actual distance that the object would travel. What if I wanted to find the speed at that moment? What if I wanted to find the equation of the tangent